And here we are again. It's the physics video lecture. Physics 2B video lecture 7. Okay, so I'm going to start with some announcements. And the first one is the posting of the video lectures. I'm going to repopulate the entire list, but in the current week I will always just have one up at a time. So this is the video lecture 7, and when this one is posted, 6 will come down, and then when 8 is posted, 7 will come down. But in the following week, everything will come back up, and we'll take it that way. I just want to make sure everybody does the work Mondays, Wednesdays, and Fridays, because this subject simply requires a steady workload in order to learn the material, okay? You can't just put it off to the end of the week, and so I'm just helping you out in that way, okay? So each lecture will be up a couple days, then it'll come down, the next one will come up. A week later, they'll all be up. That's the way it's gonna be. Good, so we have that. I had some homework problem requests, and they're exactly what I wanted to talk about anyway. So at the beginning of each class, I'd like to talk about some homework that's been turned in. In this case, it's Chapter 2, 45, 50, and 57. Chapter 2, 45, 50, and 57. 45, 50, 57. Yeah, so let's have a look. First of all, these are about vertical throws. So let's put the free fall formulas right up here for starters. Free fall, I'm really just talking about the kinematic formulas. So we have x equals x0 v0t minus and half gt squared. V is v0 minus gt v squared, v0 squared minus 2g x minus x0. One of these problems I'll use the ones with plus acceleration, but for now we'll talk about free fall. So yeah, we're talking about positive x direction being up. So I'll look up these problems here. End of chapter 2. 45 was a vertical throw. And this is the one they were asking me for 45D, velocity when it returns to the level from which it started. So we're just going to graph it. We'll graph problem 45. And then you can remember how to do the analysis. So I'm going to graph position versus time and velocity. This is in meters per second versus time in seconds. And this is in meters. Okay. So the vertical throw principally has x0 at the origin, and it's that parabola there. So at the highest point, that was t sub air divided by 2 in the previous lecture, is when this velocity comes to 0. So I'm going to graph, well, okay, let's write down what we have here. We have x equals, I'm factoring out a t, and I have v0 minus gt divided by 2. So I've rewritten the first equation, and down here v is v0 minus gt. So v0 minus gt is the equation of a straight line. And the question is how fast it was going. This is v0, and when it returns back to your hand, it's gone up and come back down. It just has that negative of that initial speed. So this is minus v0. I'll put absolute value just to make sure it's the negative of what it was up here when it comes back and hits your hand. Otherwise, all these questions can simply be answered by analyzing. Just to go back to the problems that I have in front of us, we were given 25 meters per second. We want to find how high it rises, how long does it take to reach its highest point, how long does it take the ball to hit the ground after it reaches highest point. Yeah, so all of those questions, A through D, are just obtained by the analysis of these formulas right here. Okay. So you're given V0, and then T air, I'll remind you, T air is equal to 2V0 divided by G. Always write that down before you plug in numbers. I'm not going to plug the numbers in for you on one like this. You see, this was given, G is 9.8, you're ready to go. That's when you hit the ground again. So half of that time takes you to the highest point. Okay? Half of that time takes you to the highest point. You go into this graph here, V equals 0, comma, when the right side is equal to 0, when T is equal to V0 divided by G. See, that's half of this one because it doesn't have the factor of 2 in front. Okay, good. So that's problem 45. Let's see what we had on problem 50, B and C is what they're asking for. 50, B and C was interesting as well. So that's the mailbag being released from the helicopter. Again, I'm going to do this graphically. So what's interesting here with problem 50 is that it's x equals x0 plus v0t minus a half gt squared. But the helicopter is descending. So if the helicopter is up here at x0 when time is t0, we actually can write that we have minus v0t. So if I put a minus sign in the magnitude, okay, so that's, instead of going up and back down, the graph is actually like this, okay, but we have v equals v0 minus gt for the velocity function, or v is equal to minus v0 minus gt. Again, because the helicopter is descending, it's as though it were being thrown down in the downward direction. Okay. Okay. So this is the helicopter and the mailbag. I mean, no, this is the speed of the helicopter descending, but this is the speed of the mailbag being dropped because it was released with a downward direction, okay, with a downward initial speed, okay, negative initial speed. So I put it in by hand like that. Okay, let me move on to problem 50, what was that, 7. Problem 57. So 57 was a bullet being fired and penetrating a board. So it has V0 on this side, and it comes through, it has V final. And it's slowing down, so V final is slower than V initial. They gave us some numbers, large numbers, 4, 3, good. I'm not worried about the numbers. You guys can plug those in. But I will explain this one. So this time we're using equation 3, but it's not a free fall problem, so we're just using V squared is equal to V0 squared plus 2a x minus x0. And we can let the thickness be x minus x0. When we strike it here, we emerge on that side. Okay. So we want the acceleration. Solve for acceleration. Make sure that's what we want here. Find the acceleration and the total time that the bullet's in contact. So the acceleration, solving this here, is going to be v squared minus v0 squared divided by 2x minus x0. And now you have the final speed minus the initial speed, both of them squared. Square them first, then subtract 2, and that's the thickness of the board. Okay, so you get that, and what you'll notice is acceleration is negative because it slowed down. It was going faster here and slower here, therefore the acceleration was actually negative in the other direction. When we talk about forces, we're going to run into this again. Now the time we can do the following. We can do distance times squared law. In particular, the distance is the thickness of the board, okay, equals a over 2t squared. Okay, so now we found the acceleration. That way we can say 2x minus x0 divided by a, take the square root of that. That'll be the time that it was in contact with the board. There's another way, by the way, but I'll go ahead and leave it this way. We could also, you know what, I could also say also v equals v0 plus a times t. And in that case, since we know these two speeds and we just found the acceleration, we can solve for the missing time that we're asked for. And it'll be the same answer as this. In fact, if you have time to work this problem both ways, it'll do you no harm, and you'll actually learn something there. Two different ways to get the answer. So yeah, this was the bullet penetrating the board, and I'll leave it at that for our homework review. One thing, these free fall problems, we're still getting more practice on them, okay? Because in chapter 3 we get excellent practice on the free fall, so we haven't seen the end of these yet, okay? Good. Now I'm ready to talk about what we left off with last time. So we were talking about vectors, first of all, and then vectors and motion. Now I'm not going to spend much time on vectors, much more than I did, because in this and the following chapter we'll get much more practice on vectors. So the discussion of the vectors is being spread out a bit. But what we did end with was the idea that position is a vector, velocity v equals delta r over delta t is a vector, and acceleration is just by the fact of how they were defined. Acceleration is delta v over delta t. So it follows, if position's a vector, then velocity and displacement actually belongs here in this list as well. Position, displacement, velocity, acceleration. They're all vectors. So we definitely have to know how to work with them. And vectors add like arrows. Okay. So a little bit of trigonometry, a little bit of understanding of triangles, and you can invent the vector algebra that we were talking about last time. In other words, you don't have to memorize it so much as just recognize it, practice it, and it'll just be present. Good. So these are all vectors, and our next task, we just did a couple vector problems. We want motion of a projectile. A projectile is something that you just throw. Tennis ball. I'll bring the tennis ball and the little toy cannon with us next time. But right now I'm just going to draw everything. So really our vertical throws were already a projectile. But this time we're actually going to pursue the motion of a projectile in space. So we're no longer graphing position versus time, but this is the horizontal dimension and this is the vertical dimension. And if I launch a ball, say I release it from my hand at this height, what does it do? Follows an arc and it lands on the ground over here. And I like to draw these little tennis balls like so. So every unit of time, you can see this ball traveling through the air and then it lands there. First things first, no friction. The discussion we're having here is just like free fall. There's no friction, no wind resistance, or negligible wind resistance. Okay? We have to set things up so that the friction is negligible. If I try to throw a feather, it's not really going to go in an arc. Tennis ball, baseball go in an arc. If I throw a brick, it'll go in a nice arc, and the friction will not play any role. So we're doing projectile motion. And the most important principle, which I'll demonstrate next time, I'll bring the requisite demonstration in, put it on the table here. The most important principle is that the vertical motion and the horizontal motion are independent of each other. This time I'm just going to state it first. I'll demonstrate it next time. But in projectile motion, horizontal and vertical motions are independent. What does that mean? Horizontal motion is motion with constant velocity. Vertical motion is just free fall. Vertical motion is just free fall. So motion with constant velocity in the horizontal and free fall motion in the vertical. Free fall, i.e. accelerated motion. The reason we have these two different types of motion is because the gravitational acceleration points down. So if I throw something horizontally, or if I throw something at an angle, it has what's called a horizontal and a vertical component. Okay, let's make sure we're with all motions. Constant velocity, vertical motion, which is free fall, is accelerated motion. So I'm going to do the simplest example first, and that is the horizontal throw. I always put the horizontal throw on my exams. Okay, this is one hopefully you'll learn forwards and backwards. The horizontal throw can be set up like this. I'll put the formulas left and right. Here's our picture. This is the x-axis. This is the y-axis. we're going to start from height h in the y-axis and launch horizontally with v sub 0. Okay, so initial height is h. Initial velocity v0 in the x direction. Okay. And the independence of these two motions leads us to the following formulas. So, well, actually, first of all, let's draw what we know will happen. We throw something horizontally, it's not going up, we're not launching it downwards, so it starts out smooth and horizontal and then it falls. Right? Starts falling immediately, and here's where it lands on the ground. So I'm going to label this distance d. Okay. So this could be the height of your hand above the ground, or you could be standing on a building. All depends what your choice, but you launch it perfectly horizontally, falls out like this. Now, the velocity in x is uniform, so it goes through equal distances in equal times, but the motion in y is accelerated. So here's what we have. Horizontal we have x equals v0t. That's just uniform motion in x direction. But the vertical y equals h minus 1/2 gt squared. This is simply the equation of dropping a ball. The fact that I threw it horizontally has no bearing on the vertical motion because there's no friction. Okay. So these are completely independent, the horizontal and vertical motions, and they're both easy to deal with individually. This one we've been studying, this one we've also studied. Okay. So this is the position in time of dropping something. When t is equal to 0, I'm up at h, and then as time goes on, it's falling, and this is the forward motion. What this means is, if I were to throw something horizontally and drop a second object at the same instant, okay, launch and drop, then this one would hit the ground at the exact same time as this one hits the ground. And I have an interesting demo that's going to prove that, if I can set the thing up. Okay, let's send this up there and work with these. So with these two equations, you'll notice the time is not being graphed. This is position and this is position. With these two equations, we can answer any and every question about the horizontal throw. So let's go ahead and answer some. Okay, so let's formulate the question first. Questions. First of all, the time in the air, which is to say that how long does it take for it to strike the ground, that's something we have to know. Distance d, so how far from the launch point does it strike the ground? The third question, speed v at impact, would be interesting to know, because it's moving forward, but it's also picking up speed by falling. So the speed is going to be faster at impact. for angle theta at impact, and that I'm going to draw into our graph now. So the point is this. Here, let's relabel a bit. Put the D over here. I need some room. There's the D. Point is that when the ball strikes the ground, so it's been going like this, you know, it's coming in at an angle. It started out horizontally, it's coming in at an angle, and I'm just going to draw an arrow. That's the angle it comes in. I could say the angle underneath the horizontal. In fact, you know, it's actually coming in a bit steeper. Let me do that. More like that. Okay. So it strikes the ground at that angle, and that's another quantity we want to find out. So here's the thing. This is now a two-dimensional velocity vector, and the direction is given by that angle. So we're going to have to analyze that as well. So I'll put that here as a note. Impact velocity v vector, impact speed v vector magnitude. We talked about magnitude last time. And then impact angle theta. So that's a vector. It has a magnitude, which is the speed, and there's an angle there as well. Yeah, so we're going to learn to answer all of these questions very systematically. So in particular, these first two. So the time in the air. In air, T air equals T impact. Call it what you want. That's the time when it struck the ground. From the second equation, from y equals h minus 1/2 gt squared, y equals 0. Y equals 0 when t equals what? Then you solve this, okay? So set y equal to 0, solve for t, and leave space in your notes. I'm just going to do the answer, leave some space, and come back and do it. 2h divided by g, take the square root. Right, that's the answer. Bring h over the other side, cross multiply, divide by g, take the square root. Okay. So that is t, got to make up my mind, t air. And for any given problem, of course, you can plug in the numbers and then find out how much it is in seconds. I don't do that very often in the lecture. When it comes time to our quizzes, you know, you'll actually want to solve them like this. You get to this point and then you take the numbers that have been given and you plug them in, okay? That's because we're going to have electronic quizzes, electronically graded quizzes. Good, so there's the T sub air. Our second question was distance d, okay? So we have x equals v0t, that was the horizontal motion. So the distance is v0 times the T sub air, or the impact. So this is a general formula. If I want to know how far it goes, I have to say how long it was in the air, v0 times t. I'll put a box around these. These are some great answers. So far, so good. Let's see how we're doing here. I'm going to answer these next two questions as well, and that'll bring us into the subject of vectors. So, I'd love to have everything on the board at once. Go ahead and set this up. And we're going to analyze this picture by drawing an expanded version of it. So remember, everything here is from the kinematics of free fall and just the basic kinematics of constant acceleration. So we should be able to get everything out of those formulas. So in particular, I want us to look at this. This is that distance d, and we came in this arc, and we have this vector here. I'm going to draw a larger one. I got to maintain that slope a bit better. Okay, so it's coming like that. Okay, good. So I've just drawn a larger version. And we have this vector here, vector v, with vx and v sub y. So the velocity now has two components. Where v sub x is just v0, the original speed. But v sub y came out of the fact that we had free fall. Those independent motions gave us v0y minus gt, and since it was a horizontal throw, that was 0. So v sub y is simply equal to minus g times t. Just the free fall, you drop something, it picks up speed. Right? It's just the free fall formula. I'm just giving it different letters. So when it hits the ground, so at impact, Vx equals V0, Vy equals, let me erase that, Vy equals minus G times T air. So those are our two components of this vector here. I'll draw them in red. And we would have, and the vectors add like arrows, we'd have Vx and Vy. And so what's the magnitude of V? It's just the Pythagorean theorem. It's Vx squared plus Vy squared. Vx squared plus Vy squared. Okay. So we have almost everything now. So the speed at impact, you have to take the initial speed, the speed that is gained in y direction, g times t air. It's got the minus sign, but it doesn't matter. We're going to square it anyway. And that will just be the length, the hypotenuse of this vector with its two components. Okay. And this is pretty much what we need with vectors in this chapter here. Just this business of the two components, Pythagorean theorem. And we could also get the tangent of theta to finish this off. So speed v at impact, that was part 3. And part 4, we'll just use some trigonometry. there's my angle, so I can say tangent of theta is equal to the magnitude b sub y divided by b sub x. And then we've got the magnitude minus gt and v0. Okay. But again, that comes from this drawing. So this is a really important drawing here that you recognize what's going on right here. Okay. Components of that vector. So this was the horizontal throw. I've given the complete solution to the horizontal throw. And for tonight's homework, I'm pretty much just going to assign a few of these horizontal throw problems because I want you to really understand it. So I'll just review what I did. These are all these answers. I don't need the answers anymore. You have them in front of you. Let's just draw that picture one more time of the horizontal throw. So once again, we've got our x and y axis. We launch horizontally from a height h, perfectly horizontally. I'll go ahead and label this horizontal throw. We know that goes in this kind of an arc here. Strikes the ground right there at distance d. And again, the principle is that the horizontal motion is constant velocity, the vertical motion is free fall, and the two equations do not affect each other. That's why x is just v0t, uniform, and y is h minus 1/2 gt squared. Just free fall. Just the free fall problem. Good, and the velocities have been discussed right here. So now I'm just going to look for a couple of good problems in chapter 3. Actually, before I do those problems, let me just write what's going to come next to put that into context. So after we've practiced the horizontal throw, the next one we're going to do is the full projectile motion, launch with an angle theta. And that's when I have to actually bring the little toy cannon to class and see if I can set it up in this limited area, do a little target practice. The idea next is going to be that we launch at an angle, and we'll do the whole formalism for this, and then we get that trajectory. Okay. You can see, in fact, that the horizontal throw is the same thing as this launch if you were to start at the top. Okay. Which is the reason I like to study this one first. This one's really key. I always put it on the exams. This one has more details and more interest as well. Okay, good. So homework for, this was lecture 7. We're in chapter 3, and we're looking for some horizontal throws. Let's see what we have here. This is a great chapter. Yep. So first one is problem 7. This is just someone throwing something off a cliff. Okay, horizontal throw. And it pretty much is asking everything I've just done. I'm going to give you some numbers. A couple of other versions of this problem. Like I said, that's all we want to do today. Really understand the horizontal throw. Thought there were a couple more here. Now, 54 is great, but it's a little... $54, at least have a good start at 54. 54 is tricky. Okay, I'll put a star there, but it's a couple of horizontal throw problems all in one. Okay. I would say really just try to solve it with formulas. You know, they finally give you some numbers, but first of all, just formulas. That's actually good advice for most problems. Do not worry about numbers until you actually have figured it out. You'll notice I didn't plug a single number in here, and that's a good thing. Now on problem 7, sure, you can work your way through and then plug these numbers in, which will be interesting. But definitely work your way through with pictures, labels, formulas, and algebra, the way I've done here. There may be one more good one. I thought I remembered. Here's a good one, problem 28. It's a bomber dropping bombs, and the bomber is an airplane, it's flying horizontally. So 28, we'll do part 28A. 28A. This is a good little assignment. It's all about the horizontal throw. This one here is actually a horizontal waterfall. And when water flows off a cliff, if it's not too fast, it does the same thing as when you throw something. Good. So we're going to specialize in this for this lecture. Next time we'll review these problems and we'll launch at an angle and basically try to wrap up chapter 3. It'll move on into a couple more lectures. But we're going to learn the horizontal throw and then the projectile at an angle, and that'll be good. Okay, see you guys next time.